Most BigQuery optimization advice tells you to filter early, avoid select star, and partition your tables. That advice is correct. It's also incomplete because it only addresses half what your query actually costs. In this video, I'll show you what BigQuery physically does when you run a query. By the end, you will be able to open an execution plan and read it like a story, and you will see why the half of the picture most advice ignores is half your team actually pays for. I'm Lasha, and this is Pipeline Patterns. There is a tab in the BigQuery console called Execution Details. Most users have never opened it. That's not a criticism. It's hidden behind a tab full of unfamiliar terms showing numbers with no obvious meaning. You can use BigQuery productively for years without it, and most people do. But the panel shows exactly what the engine is doing with your query, physically, stage by stage, worker by worker, and it makes a real dividing line. Without it, optimization is a pattern matching. You apply rules like filter early and hope. With it, optimization is reasoning. You can see why a stage is slow and you know what to do about it. Let's start at the bottom. When you run a query in Postgres or MySQL, you're sending it to a server, machine with cores, memory, and disks. Want it faster? Buy a bigger machine. BigQuery doesn't work that way. There is no servers you provisioned, no node count to choose. You submit work and Google's infrastructure finds available compute and runs it. The unit of compute is called a slot. Think of a slot as roughly one core CPU with some attached memory. The unit of work is the slot second, one slot working for 1 second. So a query using 100 slots for 5 seconds consumes 500 slot seconds, regardless of query time. This is the fundamental measure of computational cost in BigQuery. When the panel says total slot milliseconds was 8.4 million, that's 8,400 slot seconds of work, summed across every parallel worker. One consequence matters most. You don't control parallelism. You can't tell BigQuery to use 200 workers. The engine decides itself. So optimization here isn't about commanding the engine. It's about writing queries that map cleanly onto its execution model so the defaults work in your favor. So what does the engine actually do with your SQL? It doesn't run it as one monolithic computation. It decomposes into a directed acyclic graph of stages. Each stage is a unit of work. Read these rows, hash these keys, aggregate this column. Stages have dependencies. Stage 3 might need the output of stages 1 and 2 before it can begin. Inside each stage, work runs in parallel across many workers. Take this simple query, sum of ordered totals by region, filtered to this year. BigQuery turns it into roughly 4 stages. Stage 0 reads the matching partitions and keeps only the 2 columns we need. Stage 1 hashes the rows by region and redistributes them. Stage 2 computes the sums, and Stage 3 consolidates and writes the result. That redistribution step in the middle, Stage 1, is where we need to slow down, because that's the most important concept in this entire episode. It's called a shuffle. Here's the problem it solves. Say stage 0 reads 10 billion rows across 1,000 workers, and the next stage needs to group them by customer ID. All the rows for a given customer are scattered across those 1,000 workers, but to aggregate them, they need to end up on the same worker. So every upstream worker hashes the grouping key of each row, and based on that hash, sends the row to a specific downstream worker. 1,000 senders, each shipping data to every receiver. That's shuffle. And here's the thing. Shuffles are the dominant cost in distributed analytical queries. Not because hashing is hard, hashing is cheap, but moving data across a network is fundamentally slower than processing it in memory. The computation is rarely the bottleneck. The movement is. Once you see shuffles, something clicks. Why do we need to filter or aggregate early? Because there are fewer rows to shuffle. Why do we avoid joining at a fine grain? Because there are fewer rows produced, fewer shuffled. Why do we denormalize repeated joins? Because we avoid the shuffle at all. Why do we pick partition and clustering keys that match your queries? Because we read less data, so less data is shuffled. Every piece of BigQuery optimization advice you've ever read traces back to the same root: make shuffles smaller. It's one principle applied to different points in the query's lifecycle. Shuffles have a failure mode called Skew. Suppose your partition key is customer ID and one customer has 50 million events while the next largest has 50 1,000. The worker that receives the hot customer's packet gets 1,000 times more data than everyone else. The other worker finishes in seconds, and then they sit idle while one worker finishes. The stages of all time equals the slowest worker's time. This is why the execution details panel shows you both average and maximum compute time per stage. If max is way above average, 10x or 100x, you have skew. That's not a guess. The panel is telling you directly. Keep this one in mind because it comes back at the end of the video. In capacity pricing, skew is doubly painful and we'll see why. Now we can talk about joins properly. BigQuery has two main strategies and their choice depends on the size of the smaller side. Strategy 1 is the broadcast join. If one side is small, BigQuery just sends a full copy of it to every worker handling the big side. The big table never moves, only the small one does. Cheap, fast, and preferred. In the execution plan, it shows up as join each with all. Each is the big side, all is the small side going to all workers. Strategy 2 is the hash join. Both sides are too large to broadcast. So BigQuery hashes the join keys on both sides and shuffles both tables. So matching keys land on the same worker. In the plan, join each with each. Both sides move across the network. This is the expensive one. The rough thresholds, under about 100 megabytes, almost always broadcast join. Over about a gigabyte, usually hash join with a shuffle. In between, it depends on the optimizer's estimates. And that word, estimates, is where it gets practical. The optimizer chooses the join strategy before running your query based on what it can predict. If your CT filters a huge table down to a tiny result, the optimizer may not know the result is tiny. It estimates from the unfiltered size. So a join that should qualify for a broadcast gets a full shuffle instead because the estimate was wrong. This is why materializing an intermediate result to a temporary table sometimes produces a better plan. You are not changing the data, you are giving the optimizer accurate information. BigQuery now knows the table is small and broadcasts it cleanly. You pay for the materialization, so it's a trade-off. But when you join that same filtered set repeatedly, it pays back. You now have the full vocabulary. Slots, stages, shuffles, broadcast versus hash joins. That's genuinely most of what you need. Remember, query optimization and reading execution plans isn't magic. It's a pattern recognition. Now the part where most optimization content stops being useful. On-demand pricing bills you on one thing: bytes scanned from storage. Not slot consumption, not shuffle volume, not wall time. Which means a terrible query that scans 10 terabytes and a great query that scans 10 terabytes cost exactly the same, even if one runs in 30 seconds and the other in 30 minutes. That's why all the standard advice is about reducing bytes scanned. Under on-demand pricing, that's rational. But in capacity pricing, you reserve a fixed pool of slots, say 500, and every query in your team shares it. Now, bytes scanned doesn't directly matter. Slot consumption does. A query that hogs 400 slots for 10 minutes starves every other query in the reservation. They queue or they lag. Every operation has two costs: bytes scanned cost and a slot consumption cost. Most advice you read addresses only the first. The execution model, everything in this video, is how you reason about the second. So here is the habit. The next time you run a non-trivial query, open execution details, find the stage with the highest slot time, compare max against average, trace the data volumes from stage to stage, and try to tell the story of what the engine did. That habit of reading the plan instead of just trusting the result is what separates people who use BigQuery from people who understand it. If you want to go deeper into how cloud warehouses work mechanically, the written version of this video is on my Substack, link in the description. Thanks for watching.